In this video, I'm going to show one approach to finding a numerical approximation to the Gaussian cumulative density function. So the reason why we can't just use a normal approach to this function is that this function does not have a closed form solution. So we have to use a numerical approximation. Now the function is written as capital Phi of x, and it's equal to the integral from minus infinity to x of the Gaussian probability density function. Now, the Gaussian function is a lowercase phi, and it has the following density. Now, one thing that I'll just show you quickly is that the derivative of this, and I'm sorry, that should be a t here, the derivative of this is equal to this times by this, because remember with the exponent, the derivative, it will keep the same exponent, but then we have to multiply here by minus 1/2 times 2t, which is minus t, and that is actually equal to minus t, and then what we started with. So we have this key fact here, which we will use a little bit later on. And so what we decide to do is we rearrange or rewrite this as the integral from minus infinity to 0 of phi t dt plus the integral from 0 to x. Now actually x can be less than 0 and it will not cause a problem. So we rewrite it like this. And what you'll know, or you may know, is that the integral between minus infinity and 0 of the normal density function is equal to 1/2 because it's symmetrical about 0, so half the density is on this side. So here we can replace this with 1/2 plus the integral between 0 and x phi t dt. And we can again rewrite this as equal to 1/2 plus 5x integral between x and 0 5t dt divided by 5x. So all we've done is we've multiplied and divided by 5x. And because the density function is always greater than 0, it's perfectly fine to divide by it, and we know we're not dividing by 0. And now I'm just going to introduce a bit of notation. So we are going to just write the term here, this particular term, as b of x. So b of x is equal to the integral between 0 and x of 5t dt divided by 5x. So we can actually say that b of x times by 5x is equal to the integral between 0 and x phi of t dt. Now we can differentiate both sides, so we get b dash of x 5x plus phi dash of x b of x is equal to And now for the right hand side, when we differentiate this, if we have a small change in x, then the integral is actually going to increase by the value of the PDF at the point at which we added that little extra bit on. So this is what it's going to be equal to. And as we showed earlier, phi dash of x is equal to minus x phi of x. So we can rewrite this as b dash of x phi of x minus x phi of x b of x. And so that's equal to phi of x. And then, as I said, phi of x is not going to be equal to 0, so we can divide by phi of x. So we get b dash of x minus x b of x equals 1. And so from this point, we can just continue on differentiating with respect to x. And so we get b double dash of x minus, and then we actually know what we want to do first is we just want to simplify or express this with b dash of x on its own. So we'll write b dash of x is equal to 1 plus x b of x. So we've just moved the x b of x onto the right hand side. Now what we can do is we can differentiate with respect to x. So we can go b double dash of x is equal to x b dash of x plus b of x. And we can keep doing this, so we get b triple dash of x equals x b double dash of x plus 2 b dash of x. And the reason it's 2 is because we get 1 b dash of x from here, and then we differentiate this x to get a 1, and we multiply by b dash of x here. So we've got 1 b dash of x plus 1 b dash of x is 2 b dash of x. And we can continue on doing this, and what we will find is that b k, so the kth derivative of x, is equal to x b k minus 1 of x plus k minus 1 times b k minus 2 of x. So this is another important formula that we can kind of use. And so in particular, we really want to use that formula when we're going to use it in a Taylor expansion, and we only really need to use it around 0. So I'm going to just clear or move the screen, and then we can continue going. So let's see. We want to know these values, but when x equals 0. So we're going to say, right, b of 0 equals 0. And that's just because this is the integral between 0 and x, which is 0 of some function. And the integral between 0 and 0 is going to be 0, because there's not going to be any area in that. So now we can go on and look at b dash of 0, and that is going to be equal to, as we saw up here, that's going to be equal to 1 plus x b of x, so 1 plus 0 b of 0, so that's just going to be equal to 1. Then b double dash 0 is going to be equal to 0 times b dash of x plus b of x, which is b of 0, which is 0. So it's 0 plus 0, So we just get 0 there. Then we've got b triple dash 0 is equal to x, so 0 times something, plus 2 times b dash, so 2 times 1. So it's going to be 2 times 1. Then b4 of 0 is equal to 0 again, and the pattern continues. So for this one we get b5 of 0 equals 0 times something, plus 4 times b3 of x, so 4 times 2 times 1. And we can keep this going, and in general what we will find is that b k of 0 is equal to 0 if k is equal to 0, 2, 4, and it's going to be equal to k minus 1 times by k minus 3 times by 2 if k equals 1, 3, 5, and so on. And this is equal to 0, and this is equal to k minus 1 divided by 2 factorial times by 2 to the power of k minus 1 over 2. And k minus 1 over 2 is guaranteed to be even. So we just, you should be able to work out why this is the same as this line. And so we get this for k is 0, 2, and so on. Here for k is equal to 1, 3, and so on. So now the next thing that we want to do is we want to use a Taylor series expansion. So the Taylor series says that b of x is roughly equal to the sum from n equals 0 to infinity of b dash or bn of x divided by n factorial times by x to the n. And actually that is a little mistake. This x here, let's see there, that should be bn, because we're taking the Taylor series about x equals 0. So it will be the nth derivative evaluated at 0 divided by n factorial times by x to the n. And that is our approximation of bx. And now we can actually use something that we know, which is that bn is only non-zero for n is odd. So we can actually exclude some terms from this and just rewrite it as the sum from n equals 0 to infinity of b 2n plus 1 of 0 divided by 2n plus 1 factorial and then x to the 2n plus 1. And so because the sum is to infinity, we don't need to explicitly say we've gone from n equals 1 to 3 to 5. We can just say from 0 to infinity, but we multiply by 2 and add by 1 each time. So we've excluded all of the even terms from this sum. And then now we can actually substitute in the value that we worked out for b to the 2n plus 1, or b, that derivative. And because we know it's always odd, we know it's always going to be the value that we worked out here. So that is equal to the sum from n equals 0 to infinity of, and now we sub in 2n plus 1 for k, so we get n factorial here times 2 to the n. And that was the b part, or the b of the 0, and then we divide by 2n plus 1 factorial, and then we have this term. And we can simplify that a tiny bit more, or, well, it's actually not really simplifying it. We can make it a bit more obvious exactly what it's saying by expanding it out a bit. So it's the sum from n equals 0 to infinity of 2 to the n plus 1. Oh, sorry, not 2 to the n, 2n plus 1, 2n minus 1. And we keep going until we get down to 3 and then 1. And these are the terms that we've got from this part, and then we multiply that by x to the 2n plus 1. So that's our approximation for bx. And now if we refer back to the very beginning, we said that 5x, the cumulative distribution function, is equal to half plus small 5x, the PDF, times b of x. So if we just rewrite that now using this approximation for b of x, what we'll get is that the cumulative density function is roughly equal to 1/2 plus the probability density function times by the sum, and I'll use the more compact version that we found here, from 0 to infinity of n factorial 2 to the n over 2n plus 1 factorial x to the 2n plus 1. And this is the Taylor series approximation for the Gaussian cumulative density function. So if we don't fully try to calculate the sum, and we just cut off the sum at some value, like say 10, so we take the sum from n equals 0 to 10, that would be an approximation for the CDF.